We're going to be talking about lines that intersect circles. Really, it's just properties of circles, various ways that lines and circles can intersect. We're going to identify tangent, secants, and chords, use properties of tangents to solve problems. We're going to be looking at interior of circles, exterior of a circle, chord, a secant, a tangent, a point of tangent, congruent circles, concentric circles, tangent circles, and common tangents, and so much stuff you can't believe. Y'all still writing? Give you a chance to go back later. All right? Because what I really want you to hear is this. A circle, you might want to write this part down, what I underlined. A circle is just the set of all points in a plane that are equidistant from a given point, and we call that point the center of the circle. So I didn't record that. Circle is the set of all points in a plane that are equidistant from a given point. We call this the center of the circle. Interior is inside the circle. Exterior is outside the circle. Move on. All right, you need to write the entire slide down right here, okay? This entire slide's really important. I would also encourage you to draw or, draw the figure as well, all right? And label it. Okay, so I tell you what, y'all draw it, and then we'll talk about it. All right. So a chord is a segment, a line segment, whose endpoints lie on a circle. When we look at a circle, I'm going to use the word rim to talk about the edge of the circle. Okay? Very simple. Does anybody not know what a basketball rim is? Does anybody not know that a basketball rim is circular? Okay, good deal. All right. So when I talk about, I'll talk about rim. Okay. It's probably called the edge of the circle or the outer edge. I'll use it and try and make sure we can grasp it a little bit better. All right. The rim of the circle. So a chord is a segment, meaning it starts and stops on the rim. It starts and it stops on the rim. Okay. It does not go outside of the interior of the circle. A secant, though, is a line that intersects the circle at 2 points. So somebody tell me in your own words the difference between a chord and a secant. Yo.
One is from rim to one side of the rim to the other side of the rim, and the other one just goes completely through.
Very good. Okay, one keeps going, right? The secant keeps going, right? It touches both rims, but it goes on forever, okay? Tangent is a line in the same place as a circle, or in the same plane as a circle that intersects it at exactly 1 point. Okay? It just nicks the rim. Okay? And that point where it hits is called the point of tangency. Are you with me? Good news for you guys. Really good news. About 80% of this unit deals with one of those 3 things. Chords, tangents, secants. Chords, secants, tangents. Okay? Got me? We're going to learn a whole bunch about them. We're going to talk about angles. We're going to talk about volume. We're going to talk about how there's all sorts of principles dealing with circles and intersecting lines and all sorts of stuff. So we're going to really expand it, but about 80% of it goes back to one of those 3 things. Okay? So these are the core basic concepts of a circle. All right. Real quick, let's identify each line or segment that intersects circle L. Chord. Line segment JM. Let me turn the lights off, make sure y'all see this. The difference between line segment JM and line JM is the difference between a chord and a secant right here. Okay? Everybody got me? This goes all the way back to day 1. We said, hey, if I wanted to talk about JM as a line segment, I would say start at J, go to M. Right? Don't go any further than J to M. Remember that? And those were the definite beginning and end points of a segment. In this diagram, if you start at J and you go directly to M, and you go no further, then you have a chord. If you go beyond that, you have a secant. Okay? Everybody get that? That's the difference between a chord and a secant. Remember, Anthony just said it last slide. He said it goes, a secant keeps going, right? In both directions, it'll keep going. Okay? So that is the difference between a chord and a secant. Your tangent is line M in this case. The point of tangency would be H. Let me go back to this now. KM was also a chord. Starts at the rim of the chord, ends at the rim, starts at the rim of the circle, ends at the rim of the circle, goes inside the circle. Sounds like a chord to me. It's a special type of chord, though, because it passes through the center. And since it passes through the center, it's a diameter. All right? Here's the principle. Every diameter is a chord. Say it again. Every diameter is a chord. Not every chord is a diameter. As a matter of fact, in this case, it's just one of them. Okay? But every single diameter, by definition, is a chord. It's a line segment that starts and stops on the rim of the circle. It just so happens that it's a special type of chord because it passes through the center of the circle. Okay? Everybody got me on that? Radius. Radii. This is the easy one, right? Come on now. Y'all got to make sure you get this one down, right? Lateral, you with me? L to K, L to J, L to M. All radius, right? Definition of a circle. The definition of the circle is set of points that are equidistant from the center. We call those the radii, okay? So if you go from the center of the circle to the rim of the circle, you got the radius, all right? Huge principle. It is my goal to tell you this every day for the next 2 weeks. It's one of those things you're going to remember forever. All radii are created equal. All radii are created equal. To be a circle, the distance from the center to the rim has to be the same. If it's not, you don't have a circle. To be a circle, the distance from the center to the rim has to be the same, all the way around the circle. And that means that all radius have the same measurement inside of the circle. Everybody hear me? So if L to K is 5 feet, what would L to M be? L to J, L to H, L to over here, L to anywhere on the rim of the circle. It's got to be 5 feet. All radii are created equal. Everybody got that? All right, your turn. I'm going to give you 3 minutes. I want you guys to give me an example of each. Tell me true or false. You ready? A chord. I've got 2 of them that I see. QR. Is that a chord?
Yes.
Is line segment ST a chord?
Yes.
Yes, it is. Okay? Now let's talk about a secant. Is line ST a secant?
Yes.
Do y'all see the difference between line segment ST that starts here and stops here, and line ST which starts over here in infinity, goes through point S, through point P, through point T, and it stops somewhere up here in infinity. Actually, it never stops. Y'all got that? That's the difference between a line and a line segment. Tangent. What would be your tangent? Yeah, UV. Okay? UV. You could write it as line UV. You could write it as line segment UV. It don't matter. UV is your tangent. U is the point of tangency. I know it's not up there, so don't worry about it, but you should have picked up on U is the point of tangency. The diameter, ST. Is ST a chord?
Yes.
Yeah, let's get used to this, guys. If it's a diameter, it has to be a chord. You hear me? You might want to write that one down. If it's a diameter, it has to be a chord. One more time. If it's a diameter, it has to be a chord. All right? And then we got some radii here. Let's start in the center and work our way around. I got PQ, PT, PS. If I wanted to, I could have said PR, PU, but that stinks. Okay, just kidding. Just kidding. Just some bad jokes. All right, y'all write this one down for me, okay? All right, two circles are called congruent circles if and only if they have congruent radii. That would make sense, right? Think about it. If AC is congruent to BD, that means that you have congruent circles, okay? Now we'll get into why that's true a little bit when we talk about sector, but remember the area of a circle is going to be pi times radius squared. So if the radius are the same, you're going to have the same area. If you have the same area, that means you're talking about the exact same figure, okay? Concentric circles are coplanar circles with the same center. So concentric circles, okay, just one circle inside of another circle. Could I have 3, 4, 5? Have y'all ever seen like a bullseye target or a dartboard? Concentric circles, right? Yeah, you have as many as you want, all right? And then coplanar circles that intersect at exactly one point, we call those tangent circles, okay? Notice they could be either internally tangent or they could be externally tangent. Everybody with me? Okay? All right. Moving on. Get them? Good? No? All right. Let's move on because we got a little bit more. Find the length of each radius. Identify the point of tangency. Write the equation of the tangent line at this point. All right. Here's how I like to find radius. Okay? Right now, here's an example of what I would do. I would go, like, put my finger in the center and count 1, 2. And that's what I do, okay? You can do it your way, but my way is pretty good, okay? What about right here, Mr. Hobbs, where it's stuck in the middle? You're right, it is. You go 1 1/2. Okay. Sometimes it's tougher. Guys, we'll 1/2 and a 1. The real way, if you want to know, find the diameter. Cut it in half. Diameter. 1, 2, 3. Correct? Diameter would be 3. You cut the diameter in half to get the radius. Right? Diameter. 1, 2, 3, 4. Cut it in half, you get the radius. Okay? So, that's how I would do it if I were you. Okay? But, you don't have to. If you're desperate to know mathematically how to do it, wait about 3 weeks. We'll talk about equations of circles. X minus h squared plus y minus k squared equals radius squared. And you'll be doing it as much as your little hearts want to, okay? But just hold tight for me for now, all right? And then it wants the equation of the tangent line at this point, as it's just what the warm-up was, correct? Where are they tangent? They're tangent along the line where y equals 0. Mr. Hobbs, that's the x-axis. You're right. Go back to the warm-up. The horizontal lines are written as y equals, right? The vertical lines are written as x equals, okay? Don't forget that. You got me? All right. Common tangents. A common tangent is a line that is tangent to 2 circles. In this case, line L is tangent to both circles A and B. As well, line M is tangent to circles A and B. So this has got 2 common tangents. Okay, line L and line M. Next slide, same thing. You don't have to rewrite it, just know. These are also common tangents, right? Same thing, it fits the definition. Line P is tangent to line or to circle A and B. It hits different points, but it's still tangent to both of them, right? Line Q is tangent to A and B. Okay, you got me? So both of those are still common tangents. As long as it fits that definition, you're okay. Then we get to this theorem, which you need to write down. Okay? This is a really, really, really important one. Right? Really important one here. Make sure we're clear on all of this. If a line is tangent to a circle, it is perpendicular to the radius drawn to the point of tangency. Likewise, if a line is perpendicular to a radius of a circle at a point on the circle, then the line is tangent to the circle. When I say perpendicular, what type of angle is formed? A 90-degree or a right angle. Okay? This is why I was telling you it's so vital that you understand point of tangency, right? If that point B is inside the circle at all, then you don't fulfill the radius, right? Because the radius has to go all the way to the rim of the circle. And if you don't have your point of tangency at the rim of the circle, then this theorem is not true. And if this theorem isn't true, we in trouble. You'll see why later, okay? Yes, if you want to know, you're going to be going from C out here, forming right triangles like crazy, okay? I'm not going to do that to you today, but just know that's coming. All right. The fact that the radius and the tangent line form a 90-degree angle will be a baseline to get to a whole bunch of theorems, all right? And effectively solve a bunch of problems about circles, okay? What you're going to end up seeing, guys, is you're going to end up seeing a slew, that means a bunch, of problems that look like that, right? And you're asked to find the distance, or you're asked to find angle measurements, and we're going to be able to go into a lot of different theorems involving those particular principles, okay? All right, move on real quick. I'll come back to it later if you need it, okay? If two segments are tangent to a circle from the same external point, then the two segments are congruent. So in this case, I've got two different tangents, point B and point C. And if point B and point C meet at the external point A, then that means that line segment AB is congruent to line segment AC. Okay? All right, y'all. So if two segments are tangent to a circle from the same external point, that means that they're congruent, right? So here's what that's going to mean. It means that the distance from A to B has to be the same as the distance from A to C. Remember our definition of congruency. Congruency means identical or the same or equal. The exact same thing. If we're talking about a distance measurement, then that means that it's going to be the same. So if I say that AB is 15.4, what is AC? 15.4. Okay. All right. In this case, it says HK and HG are tangent to circle F. Find HG. Guys, if they're tangent to the same circle, then they are congruent to each other. Take 4 plus 2a, set it equal to 5a minus 32, solve for a, substitute a in, you'll have your answer. Okay, that's all that they do right here. 5a minus 32 equals 4 plus 2a, subtract 2a from both sides, add 32 to both sides, a is 12, plug in a, 4 plus 2 times 12, that's 4 plus 24, 4 plus 24 is 28. Take you about 30 seconds to get through all that. Alright? Everybody with me? Any questions? Anybody need any other slides?